days. And we've adjusted the schedule of these sessions to somewhat accommodate different time zones. So today is aligned with East Coast time, tomorrow will be aligned with UK and EU time, and on Saturday we'll have a West Coast oriented schedule. Now, because there's 5 different sessions, please do remember that there's a different link for each of these 5 sessions, and you'll have to sign into them separately. You'll notice that there's a chat here where there's both a tab for chat and a tab for Q&A. If you would like to ask a question during one of the talks, just post your question in the Q&A. The session chair will monitor these questions and will either interrupt the speaker for a question or, more commonly ask it towards the end. Let's see, posters will be on Thursday and Friday. I think you've already gotten acquainted with the virtual ballroom format here. So you can sit down at a table. Poster presenters will be sitting at a table with their name marked underneath the table. And so then you can just sit down and ask the presenter questions about their poster. Okay, with that, I will hand it off to Vikash.
Thank you, Jan-Willem. So we'd like to provide a little bit of information and transparency about reviewing this year and to ask for help with community governance over in future years. So this year, like with ProbProg in 2018, the organizing committee lightly reviewed abstracts just for topicality and correctness. So there were a small number of rejections, I think 5 this year, primarily for work that wasn't in scope for the conference. As a result, the proceedings aren't archival. This allows authors to discuss work at the conference, even if it's preliminary. Now, we had worked towards organizing probabilistic programming this year, ProbProg 20, with governance from a formal steering committee of senior researchers and with reviews provided by program chairs and program committee members for the community. But we were unfortunately unable to formalize this early enough that that structure could govern ProbProg 20. We now have confirmed help from senior members of the AI, statistics, machine learning, and programming language communities to transfer the conference to be governed by an independent organization. We're going to need lots of help from all of you and the broader community to do this. We're planning to have a PL-style structure with a general chair who's responsible primarily for logistics and program chairs from the independent research communities that are intersecting at Prob, who are responsible for the scientific program. And we'll be, of course, soliciting reviews from, or the general chairs and program chairs will be soliciting reviews from program committee members drawn from the community at large. So over the course of this conference, we'll send out a formal request for community nominations for program chairs and committee members for the next ProbProg and subsequent ProbProgs. I'm also really happy to say that Jan-Willem and Jean-Baptiste have volunteered to provide continuity by serving as general chairs next year. Over the longer term, the steering committee is also helping create a venue for probabilistic programming research that's differentiated from other top AI, statistics, machine learning, programming language venues, and developer conferences, including an online journal that got put on hold this year, partly due to the pandemic. So please send us feedback or thoughts that the steering committee can consider in putting together the journal. Now I'd like to hand it over to Jean-Baptiste.
All right, thank you. Well, so I'm going to just introduce our first keynote speaker, Leslie Kaelbling. So Leslie Kaelbling is professor of computer science and engineering at the Computer Science and Artificial Intelligence Laboratory, CSAIL, at the MIT. She's done pioneering research on decision-making under uncertainty, machine learning, and sensing with applications to robotics. She's played a key role introducing POMDPs, partially observable Markov decision processes, into AI and robotics. POMDPs are now widely accepted as the framework for engineering AI systems that make decisions under uncertainty. Over the last decades, she and her students have developed a broad range of AI techniques that rely on probabilistic inference and planning over structured symbolic representations of objects, scenes, and environments. So we're delighted to have Leslie give her keynote. Her work over the years has surfaced many central AI problems where probabilistic programming, if we can sufficiently scale it up, could make a difference. She has also played an important role in incubating pro-stick programming. For example, her students and postdocs include multiple invited speakers from the last edition of ProgProg in 2018. So Leslie, thank you very much for being here, and the floor is yours.
Thank you very much for the invitation to speak here and the kind introduction. And let me just get myself sharing here. Okay, I at this point don't have visual feedback, but I trust someone will tell me if this is not going correctly. So I'm excited to talk to you, and I want to tell you something about the work that I do that's motivated by robotics problems. And I hope also to ask for help. So at various points, I'll give you a list of some questions that are important to me that I think maybe people from this community could help me with. So fundamentally, I want to understand AI, and I use robots as a kind of mechanism for thinking about that. I want to not make a particular robot that can solve a particular problem, but understand generality. So could I make a robot that could make tea in anybody's kitchen in the whole world? You could probably make tea in anybody's kitchen in the whole world with a certain amount of looking around and a few mistakes. So how could we get a robot to do that? I'd also like the robot to be able to do any kind of a job in a house, a new thing, to learn things quickly. So how can I think about this problem? So the way I think about it is I think that my job is to be the robot factory. So I'm going to make robots that are going to go out and work in the wild. So maybe the way I think about it is that I'm going to make these robots, and the robots that I make will all have the same program in them when I ship them out of my factory. And so I have to figure out what program am I going to put in the head of my robots. And I kind of approach this decision theoretically, and I say, well, okay, so the person who ordered these robots from me had a spec in mind. And the way I want to think about the spec that they have for their robots is that there's some distribution over possible domains that these robots will actually have to work in. So maybe I think about shipping household robots, and I say, well, there's a distribution over households, what they're like, what the jobs might be, and so on. And my job as the engineer of the robot factory is to find a program that's going to work well in expectation over all of those domains. So that's how I think about the problem. And one of the reasons I like this problem formulation is that I hope that it removes some amount of bickering. Well, it's hard to remove bickering in a technical community, but there's no real need to argue about whether it should do learning or not do learning or whatever, because really, in some sense, there's a best program that I could imagine that works in expectation over all these domains. Now, coming up with the specification is hard. So that's a difficulty with this view. And another major difficulty, which is what makes me happy to be talking to people who work on programming methodology, is that we have to find a program to put in the robot's head, but it's not at all clear what that optimal program is. Right? So in some sense, we've made the job hard for the robot factory, but at least we've made it concrete. So, okay, so this is what I take to be my job, coming up with a program that I'm going to put in the head of a robot that's going to allow it to work in a wide variety of environments. So just another kind of way to think about this is you can say, well, we have a couple different dimensions that we could characterize that distribution over problems that the robot might have to solve, or environments that it might find itself in. So in one sense, one kind of degree of variability is how much variability there is in the problems the robot is going to have to solve when it's out in the world. And another degree of variability is how much we, the engineers, know about the particular domain that the robot's going to find itself in. So over here in the left-hand corner, we have kind of the classical engineering paradigm where we, the engineers, know exactly what the robot needs to do. We know, and it's not a very broad range of things. And that's really the classical engineering paradigm where we sit and write down a controller or a concrete specific program for this robot to do this specific thing. And that works great. Another point in the space is where we tend to build systems that actually do reasoning online, right? So where, for instance, one might make a planning or reasoning system because that seems to be the most compact way to describe a program that's actually going to address a wide variety of problems. But where we, the engineers, still know the domain models. Maybe we can still write down the models, we write down an inference engine, and then we have a system that's reasonably general purpose. Up here in the other dimension, I guess I would put a lot of current work in reinforcement learning, in a sense, where the factory, we don't know so much about the world that the robot's supposed to work in. But it had better not be a very complicated problem, because in general, those that, at least right now, learning methods, they don't learn strategies that are very rich or combinatorial. And where I want to be is over here in the upper right-hand corner. I would like to be able to make systems that work in domains that are very complicated, where there's a lot of variability in what the individual system might have to do, but also where the engineers don't necessarily know too much about the situation. So I want to combine learning and reasoning and live up here in the upper right-hand corner. Okay, so let's try to be a little bit more concrete. So here's a kitchen. It is not my kitchen, I promise. It's kind of a terrible kitchen. The robot rolls into this room and you might look around and say, oh man, where is the fork? Like, I don't know what to do in this world. So imagine that you had to make dinner in this kitchen or clean it up or something. What makes that a kind of a terrifying problem? So one thing is that the state space is huge. Robotics people like to talk about the number of degrees of freedom that their robot has. You know, oh, maybe it's 4 or 10 or 20. But how many degrees of freedom does this kitchen have? How many state variables are there? That's really hard to think about. There's so many. It's not just the positions and orientations of the objects. It's all kinds of things. The action space is huge. It's continuous, first of all, so the robot can move its joints in a continuous way. But more importantly, it's long horizon. The number of sort of primitive actions that the robot might have to take in order to make dinner here is huge. And there's fundamental uncertainty that will be dear to this crowd. So sometimes in the robotics community, if you say you work on planning under uncertainty, people will scoff a little bit and say, you should just get better sensors, because if you had better sensors, you wouldn't have to worry about the uncertainty. But the uncertainty here is fundamental. You know, the robot can't know what's in the stove or whether the stuff in the blue bowl is rotten or when the people are coming home just by having better sensors. It has to deliberately reason about what it knows and doesn't know and take actions to gather information and so on. So these things combine to make this a very hard problem. On the one hand, a very hard problem. On the other hand, though, interestingly, a kind of a problem that most adult humans could solve without too much trouble. So it's, you know, it's easier than Go in a way, but much harder than Go in a bunch of other ways. So how do we think about it? There's a tension, right, between the hand coding of things and the, you know, neural network learning of things at the moment. And so we really have to address this tension. And the view that we take is that we hope there are going to be some general kind of representation strategies and inference mechanisms that we can build in. And what we've been doing in the last 10 or 15 years is actually hand building a system to kind of explore architectural questions and questions about what the inference mechanisms might be. And we're now in the process of trying to do more learning, right? So to gradually take out stuff that we built by hand and see if we can put in some things that are learned. So I'm going to spend most of the time talking about the hand-built part and the probabilistic inference stuff that comes up. And I will at the end talk about some aspects of learning. So, okay, so in the kind introduction, there was a mention of POM-DPs, partially observed Markov decision processes. And so I'm going to actually just kind of describe that paradigm a little bit, because I think that I have a very broad audience here, and then how we try to address it. So fundamentally, the idea is that there's this robot that's interacting with the world. It gets observations about the state of the world, and it has to take actions to, you know, move itself around or move its camera. And we divide the problem into these two pieces. This is a completely standard decomposition where there's one module that is in charge in some sense of aggregating the robot's information state. It takes the history of observations and actions and computes a belief, some summary statistics over the history of actions and observations it's had. Generally speaking, we think of that belief as being a probability distribution over the underlying state space of the world. So that's one component. And then the other component is to say, well, given my current belief about the world state, what action should I take next? So we'll think about those two pieces. Now, POMDPs, the mathematical story of them is very beautiful. It comes from work in operations research. The optimal solution of POMDPs is really, really difficult. In a simple discrete world, it's doubly exponential in the finite horizon. So if H is how many decisions you have to make, it's doubly exponential in H. If you try to solve the infinite horizon problem, is actually formally undecidable. So for a while, I kind of thought, I have no idea how to apply this to robotics. It's so complicated. It seems like the right formulation, but it didn't help to think of my problem as POMDP because the solution mechanisms are so complex. But over time, what we've done is to say, well, okay, I accept the fact that this is the kind of problem I have, and I also accept the fact that I can't solve it optimally. And so then the question is, well, we still have to do something, right? That was what makes me an AI person maybe and not a theoretician. I still have to do something, so what can I do? And so the way we're going to think about it is we're going to think about building the best state estimator that we know how to build and actually doing pretty approximate action selection, but trying to make up for that with feedback. Okay, so I want to talk about state estimation first, just to give you an idea of the kinds of things that we think about. So we get observations from a vision system. They might be detections that tell us the pose of an object, its type, its color. We get to know the robot's configuration and how much it thinks it's moved lately. Point clouds, which are 3D models of the things it sees, maybe the mass of an object when it picks something up. And our belief representation at the moment is, you can think of it, one part of it is something like a database. It's a list of object hypotheses. Like, I think this might be an object, a chunk of rigid stuff in my world. I might have a distribution over its type. I might have a distribution over its mass, its position relative to the robot. So I have a kind of set of object hypotheses. I have some representation of the